Hello everyone, my name is Labani Malik and I am a postdoctoral research associate at Caltech. So before I begin to present this work, I would like to thank the organizers for this opportunity. And of course, thanks to the audience for attending my talk. So today I'll talk all about the least massive AGN, where the mass of the central supermassive black hole is in the range of 10 to the 5 to 6 solar mass. So this range is quite unexplored and we know very little about their accretion properties. But we can utilize this AGN to verify the mass invariance of black hole accretion and possibly spin as well. So my motivation to study the lowest mass AGN came from these two figures, where we see time delays between soft 0.3 to 1 and hard 1 to 4 kb bands as a function of frequency for both high mass AGN and stellar mass extrabinaries. In particular, the shape of their lag profiles is identical, where we notice low frequency positive hard lags and high frequency negative soft lags. So this indirectly suggests that we might get similar time lags in low mass AGN as well. So even stronger motivation comes from DeMarco's work, where we see a strong correlation between soft lag frequency, amplitude, and black hole mass for a number of AGN. So there is a good chance of discovering similar time lags in the lowest mass AGN as well. So my initial goal was to hunt for the least massive AGN in the archival data, derive their extra time lag profiles, and if soft lags are detected, then we plan to extend the black hole mass versus soft lag scaling relations from high to low mass end. And if we can safely extrapolate all the scaling relations, then that would be a confirmation for the unification theory of black hole accretion. We then plan to explore possible origins of soft and hard lags and estimate the height as well as radius of the X-ray corona from our lag measurements. Then through spectroscopy, we first identify different spectral components, in particular the soft X-ray excess emission, the origin of which is still uncertain even in high mass AGN. So here we apply our new high density reflection model to explain this excess emission and measure the electron density of the inner accretion disk. The measurement of density parameter is crucial to test the standard alpha disk model of Sakura and Tsunaev. And of course, we took advantage of our model and determined the black hole spin parameter for the least massive AGN sample, and then derive the complete AGN spin versus mass plane. Let me now introduce you to the sample that we used for our work. So they are taken mainly from SDS's AGN catalogs. After cross-matching those catalogs with the X-ray archive, mainly XMM Newton, we found a total of 29 low-mass AGN, both type 1 and type 2. For time lag analysis, I applied mainly 3 filters: background flares, filter duration, and source type, which led to a final sample of 8 type 1 low mass AGN, and they are all local radio quiet. But for spectroscopy, we did not really apply any filter on exposure time, but excluded those AGN that did not have epic PN data above 4 kV and obtained a sample of 13 type 1 low mass AGN. Again, they are all local radio quiet. So I'll first present the results that we derived through Fourier analysis. So here, basically, we measure the frequency-dependent time delays between 0.3 to 1 kV soft band, which is mostly dominated by the soft X-ray excess emission, and hard 1 to 4 kV band, that is representing the primary Paul emission. And these are the lag frequency spectra for the selected 8 low mass AGN. And we detected both negative soft and positive hard lags in 6 of them with at least 90% confidence. Then we extend the existing black hole mass versus soft lag scaling relations from high to low mass end. And we find that the updated relations are in agreement with the existing ones within 1 sigma. So we then utilize these lags to measure the height and radius of the X-ray corona. So as we know that we can interpret soft lag as a signature of disk reverberation, where the inner disk emission responds to the incident coronal emission, and the soft lag amplitude is basically the light travel time from the corona to the inner disk. The middle panel here shows the disk reverberation lags at different coronal heights in curved spacetime. And here we have corrected for both Shapiro delays as well as spectral dilution, and find that corona has a height of 10 RG for the low mass sample on an average. One more thing, we found that the height is also dependent on the black hole spin, and I'll talk about that later. The hard lag, on the other hand, we explained using propagation fluctuations inside the corona. So in this scenario, hard lag amplitude is basically the viscous time delay of fluctuations that are propagating from the edge to the core of the corona, where soft X-ray photons are coming from the edge and hard photons are originating from the core. Therefore, from the hard lag amplitude, we can measure the radius of the corona, which is around 6 RG for the sample on an average. And these measurements are in agreement with that of higher mass HEN. Then using spectroscopy, we determine various other physical parameters, for example, spin of the black hole, density, ionization state of the inner disk. So here we apply our most recent high density version of the relativistic reflection model, because when the black hole mass is low, we expect the density to be higher according to the standard Sakura and Tsunaev disk theory. And here you can see how density affects the X-ray spectra, in particular the soft X-ray excess emission. And we're still struggling to understand the origin of this excess emission, even in high mass HEN. So here I need to remind you that for spectral analysis, we had a sample of 13 type 1 HEN, and they all showed an excess emission below around 1 to 1.5 keV. And in addition, the source J1559 had a narrow iron K alpha emission line at 6.4 keV. And for POX52, we see an absorption curvature in the range 1 to 2 keV along with the soft excess. So our high density reflection model explains this excess emission for all 13 HEN, and we did not need any additional low temperature comptonization component. But for POX52, we had to include one warm absorber to explain that deficit of emission. And the average density of the accretion disk is around 10 to the 18 per cubic centimeter, which is higher, but expected according to the standard alpha disk theory. So here on the left-hand side, I plot disk density that we obtained from the fitting versus black hole mass multiplied by the square of the accretion rate on a log scale. And we see an anti-correlation between these two quantities, which is expected if the disk is standard Sakura-Tsunaev and if it is dominated by the radiation pressure. Here, blue points denote our low mass sample and red points are for higher mass HEN. The black lines represent solutions for different fractional power of the disk that is transferred to the corona. And the best fit orange line is consistent with F equals 0.7 solution, which means around 70% fractional power of the disk is transferred to the corona on an average. And this fraction agrees well with higher mass CPT1 HEN. In the right panel, I plot accretion rate versus black hole mass. The green lines are the thresholds below which the disk is dominated by thermal pressure. And you can see that accretion rates are above this dashed green line, which corresponds to F equals 0.7. So when the power transferred to the corona is below 70%, then disk becomes thermal pressure dominated. Then using our model, we measured the black hole spin parameter for the sample. And here you see black hole spin versus mass plane for the complete range of mass from 10 to the 5 to 10 solar mass. For the lowest mass, HEN, the range of spin is quite diverse, starting from 0.25 to maximally spinning with a median of around 0.75. Then we check the consistency and accuracy of our spin measurements by exploring various planes that directly or indirectly depend on the black hole spin. The first plane we studied was the disk ionization state versus Eddington ratio, which mainly depends on two parameters. One is the black hole spin, another is disk emission radius. The different lines here are the model ionization for radius from 2 to 6 RG and spin from 0.25 to 0.99. So it suggests that if the relativistic reflection is coming from within 6 RG of the inner accretion disk, then the black hole spin should be within the range of 0.25 to 0.99. And that's what we're getting from our spectral fitting as well. Then we study reflection strength versus spin for both low and high mass AGN. And these curves are basically theoretical models of maximum possible reflection strength for different combinations of density and ionization. And all four models basically imply low spin smaller s or high spin larger s. The another point is that the low mass AGN, which are denoted by blue circles, they prefer either higher density or higher ionization for the accretion disk, which is consistent with our observations. Now, if you remember that we estimated coronal height from soft lag amplitude in 6 AGN. So here we plot coronal height as a function of spin. The dependence of height on the black hole spin is in agreement with the model height expected in radio quiet AGN. So my first conclusion would be that the frequency dependence of X-ray time lags in low mass AGN is similar to that of higher mass AGN and slower mass X-ray binaries. The black hole mass versus soft lag scaling relations can safely extrapolate from high to low mass end, confirming the mass invariance of black hole accretion. Also, the height and radius of the X-ray corona appear to be mass invariant, but they are spin dependent. Not just the shape, even the origin of both soft and hard lags can be explained with the current models. The soft X-ray excess emission is well described by the relativistic reflection from an ionized higher density disk with an average density of around 10 to the 18 per cubic centimeter. We noticed an anti-correlation between density and black hole mass times accretion rate squared, which is expected for a standard radiation supported disk. The average fractional power that is released from the disk into the corona is around 70%, which is in agreement with higher mass AGN. The last but not the least conclusion is that the low mass AGN can host mild to rapidly spinning black holes. The low spin basically tells us that merger of intermediate mass black hole pairs could form the small supermassive black holes, but that's yet to be confirmed. We need to wait for the gravitational wave observatory, LISA, to verify this scenario. So with that prediction, I'll stop and thank you for your attention. I'll be happy to take any questions or you can email me as well. Thank you.